So as I said, our notes today are on Newton's first law, and Newton's first law is also known as the law of inertia. So we're going to start with the definition of inertia, and you might want to, again, have this in your notes so that you can refer back to it, because obviously if the law is named after it, we need to know what the word means. Inertia is the resistance an object has to a change in its state of motion. A state of motion is going to refer to your velocity, so how fast you're going and which way you're going. And so if you have a change in how fast you're going or a change in which way you're going, that change means that you have acceleration happening. Okay, so we could also kind of summarize it in a little bit more succinctly by calling inertia resistance to acceleration, because that's really what it is. It's resistance to changes in the state of motion, which means it's resistance to acceleration. And so the inertia that an object has is directly related to its mass. The resistance or tendency to resist acceleration is going to be related to the mass of the object. And so to illustrate that further, there's a couple of pictures up on my screen. It says you can ask yourself which object would be harder for me to accelerate. So there's two boxes, A and B. A is a box full of books. B is an empty box. Which one would be harder to accelerate? Yeah, A. You know that just looking at it, just thinking about that scenario, you should know just intuitively that A would be harder for you to get it to move. Harder for you to accelerate it, harder for you to change its state of motion, and therefore it has greater inertia, and that is solely dependent upon its mass. Okay, so the mass of the object is going to determine its inertia. Okay, so again, inertia, tendency of an object to resist acceleration. This is directly related to an object's mass, so I could ask you any number of scenarios like the ones on my screen right now, and you should be able to answer any two objects that I throw at you. So the first one says, which has more inertia, the bowling ball or the person? That's like from the video clip. Okay, so which one had more inertia? The person. You have more mass than a bowling ball. Okay, and therefore you have a greater resistance to acceleration. What about your desk versus your chair? If you're not sure, you can try to move both of them. I promise one of them's a lot easier. Okay, which one has more inertia? The desk. Okay, the chair is a lot easier to move. The desk is much more difficult. These are heavy. And so the inertia, again, is going to be directly related to the object's mass. That's how we know how to answer those questions. Okay, so again, Newton's first law is also called the law of inertia. So we've defined inertia, but in terms of Newton's first law, this is what he said. He said an object in motion will remain in motion with a constant velocity, and an object at rest will remain at rest unless acted on by an outside unbalanced force. Okay, so you've probably heard this before. Sometimes it gets summarized and shortened, and sometimes they take out important words. But an object in motion will remain in motion with a constant velocity. Those words are important. Sometimes they get left out. Okay, and an object at rest will remain at rest unless acted on by an outside unbalanced force. So obviously, the first law is referring to an unbalanced force. And so we need to talk about what it means for forces to be balanced versus what it means for forces to be unbalanced. Because in order for us to understand the scenario, we need to have an understanding of those terms. Okay, so basically, Newton's first law tells us that everything's going to stay with the same state of motion it has. It will continue moving at a constant velocity if it's already moving. If it's not moving, it will stay at rest. But it will continue with its same state of motion when forces are balanced. Okay, because it says unless there's an unbalanced force. So that will not happen when you have an unbalanced force. So again, let's talk about these two terms. Balanced forces are going to be forces that are equal in size and opposite in direction. When forces are balanced, there is no change in motion. So I have an example over here of a free body diagram showing a book. Okay, maybe it's just a book sitting on a desk. We looked at that scenario the other day. And so that book has forces acting on it, specifically the force of gravity due to Earth's gravitational field pulling down on the book, and then the support force from the tabletop pushing up on the book, that normal force. But those two forces are equal and opposite so that you have these balanced forces and the book sits there at rest. There's no change in its motion. It's not speeding up, it's not slowing down, it's not doing turning, it's just stationary. Okay, and so if you have balanced forces, you can have situations like this where you have objects that are stationary, or you can have objects that are moving at a constant speed. Both of those would occur when you have balanced forces, because if the forces are balanced, we say net force is 0. And if net force is 0, then you will not have acceleration. By the way, net force, that term, is the vector sum of all forces acting on a system. So you would simply add together the vectors, keeping in mind that vectors have a direction. So like if there were numbers associated with this, maybe Fn is positive 10, maybe Fg is negative 10. When I add them, of course, that would give me 0. Okay, if you add them by vector addition and actually draw the arrows head to tail, you're also going to end up with 0. Okay, but that's balanced forces. Equal in size, opposite in direction, they cancel each other out, no change in the state of motion. Okay, whenever we draw a free body diagram like this, we also need to make sure that we define our system. So I have here a book at rest on a table. If the system is defined as the book and table together, we can call it the book table system. So right now, this is the free body diagram I had up a second ago for just the book. If I include the table in my system, and again, depending on the question that's being asked, you might have to define your system differently in different scenarios. And you'll get the hang of trying to figure out when you have to do this. But if I had to draw the book table system, would it be the same? And again, in a free body diagram, you can only show external forces acting on your system. So that normal force that's right here is between the table and the book. If I redefine my system to be the book table system, this is now an internal force within my system. Okay, whereas this is between the earth and the book. That's still external. Okay, so Fg can stay there, but you would not be able to draw the Fn vector, at least not for the support force from the table, because now the table is part of your system. If you're in a scenario where there's a floor, then yeah, you get to draw one with the floor. It doesn't say up here, so maybe it's a table floating in space with a book on it somehow. I don't know. But it'll be more clear so you know what else you can draw. But I can tell you this, you cannot draw that normal force between the book and the table if your system includes the book and the table. That is now an internal force. Okay, so with the way it's drawn right now, no, those forces are no longer balanced. Okay, so unbalanced forces. We just talked about what balanced forces look like. Unbalanced forces will exist on a system when the net force is not equal to 0 and the forces don't cancel out. The resultant net force is responsible for a change in motion or acceleration of the system. Again, Newton's first law stated an object at rest will remain at rest, and an object in motion will remain in motion with a constant velocity unless acted on by an outside unbalanced force. So when this happens, when you have unbalanced forces, objects are going to accelerate. They're not going to stay at rest. If they're at rest, they're not going to stay at constant velocity. They're going to experience acceleration. Okay, and so if you have unbalanced forces where you have a net force, you will have acceleration of the system. You can tell in this diagram that my forces are not balanced because my force of tension, my red vector over here, is longer than my force of friction. So they're not going to cancel each other out. Friction will partially cancel out some of that tension force, okay, but they will not cancel entirely. Vertically, though, these are still vertically balanced, which would make sense in a scenario if you're dragging a book across a surface. You'd have acceleration horizontally, not vertically in that case. When we talk about net force, you do have to calculate it separately for the horizontal and vertical directions. So just like you did with projectiles and you had a whole set of variables for horizontal motion and a whole set of variables for vertical, it's very similar. You're going to have horizontal data, you're going to have vertical data, and you're going to need to use both of them to answer questions about the total net force, just like you had to for your total resultant velocity, for example. Forces that are in opposite directions will cancel out in part or in total. Forces in the same direction will add together. If a net force exists in both the horizontal and vertical directions, then a resultant net force is drawn at an angle and calculated using Pythagorean theorem or trigonometric functions, sine, cosine, tangent, all that fun stuff. You'll be doing similar things with this unit as you were doing with projectiles. Kwame, why don't you put the phone away so you can follow along with this. Okay, so again, net force, horizontal and vertical. Keep them separate. All right, so again, balanced forces, to summarize these two terms. Balanced forces tell us the system will maintain constant velocity. That means it either stays at rest, a constant velocity of 0, okay, or it moves with a constant velocity, some non-zero velocity where my acceleration is 0. So maybe it's constant velocity of +3, or maybe it's a constant velocity of -5. Okay, but you're not going to have acceleration if your forces are balanced. When your forces are balanced, that means your net force, or the sum of your forces, is 0 because they have either canceled out or you didn't have any to begin with. Unbalanced forces, on the other hand, tell us that the system will experience acceleration. So you're going to see something where it speeds up, or where it slows down, or where it changes directions due to unbalanced forces acting on that system. If you have unbalanced forces, your acceleration's not 0, you're going to have acceleration. Maybe it's +2, maybe it's -7, depends on that scenario. But you're going to have change in the velocity of the object if you have unbalanced forces. Again, that means that your net force, or the sum of your forces, is not equal to 0 because now they're not canceling each other out, at least not entirely. Okay, so they're unbalanced. All right, you also need to be able to relate that back to graphs. And I know how much you love the graphs, but we're going to go through them real quick just as a reminder. It says, the free body diagram below shows a book at rest on a table. Draw the xt, vt, and at graphs for this scenario. You should be able to tell based on the free body diagram whether or not the object is accelerating. Okay, in the scenario, you actually don't know if it's at rest or not unless they tell you. They did tell me up here that the book is at rest, but I can tell by looking at this that I have no acceleration. So the free body diagram without the text at the top, all I know is this is either stationary or it's moving at constant speed. Now because the text at the top tells me it's at rest, now I know. Okay, so if I want to show something at rest, that means it's at the same position the entire time. Its position does not change. It doesn't tell me specifically where that position is, but pick a spot. Okay, you need a horizontal line on your xt graph to show, hey, my position's not changing. It's 2 the whole time, 2 meters the whole time, okay, or whatever number you might choose. Okay, but again, in this scenario, we're dealing with a net force of 0, so we need to show a situation, okay, where our object is not accelerating. And something sitting at rest is, of course, not going to be accelerating. If it is sitting at rest, my velocity is 0 the whole time, so my VT graph, I'll have a line on my x-axis. And the slope of my VT graph tells me my acceleration. Of course, if I'm at rest, I'm not accelerating either, so I'm going to draw a line on my x-axis for my AT graph. So this is what it would look like as an example for a book sitting on a table if you were to graph it. Now again, this XT graph, I could have any y-intercept. It doesn't have to be at this spot specifically, but these other two graphs would look like this. All right, let's try another one. The free body diagram below shows a book being pulled from rest by a rope on a table. Draw the XT, VT, and AT graphs. So now I have a situation where I do have unbalanced forces. I have some amount of net force. I don't have any numbers here, but I know that I have a net force to the right. I know it's in the direction of this tension. This is larger than this. Okay, so I know my net force is to the right. And so if this book is being pulled from rest, then that means it's being pulled to the right. Okay, from rest. Then I'm going to need to show a situation on my XT graph that shows this book speeding up in the positive direction. And that's going to look something like this, where it starts out at rest, so I have this horizontal line, and then it gets steeper and steeper as it speeds up. It doesn't have to start at my y-intercept of 0, but it needs to have this shape to it. For my velocity time graph, my book is going to start at rest, and it's going to increase its velocity to the right, or the positive direction. I only deal with uniform changes in velocity, so I'm going to put a straight line that starts at 0, 0 and is positive slope, something like that. Okay, so because I'm pulling it with that tension force, I'm causing the book to accelerate, and I have a positive acceleration. I can see that because I have a positive slope. So my acceleration here, I'm going to have a constant acceleration of some positive value. Again, I don't have numbers. But everything we deal with is constant or zero acceleration. Yes, sir?
What would be an example of increase in acceleration?
We're not going to deal with anything where we have non-uniform changes in our velocity that give us accelerations that are variable, because we don't have the math to do it. If you take like the AP calculus class, whenever you have the calculus, you can do those types of questions. But for us, everything's just constant acceleration. All right. This one says, draw the xt, vt, and at graphs for the free body diagram pictured below. So now I have an object where the velocity is to the left, and I've labeled it initial velocity to the left. And I have forces acting on it. So it's moving on some surface. It doesn't say what's happening, but I have a normal force here. So maybe it's a book sliding across a desk that's moving to the left but slowing down due to friction. You can tell that friction's in the opposite direction as its motion, so it will cause it to slow down and eventually stop. Okay, and so that's what you'd have to be able to do, is take a look at this information and say, hey, this object is sliding to the left, it's going to slow down to a stop. Okay, but my net force in the x direction is unbalanced. I have a net force to the right. You'll notice that doesn't mean it's moving to the right. In fact, it's not. It's moving to the left. Okay, and it's labeled up here. So the net force doesn't tell me which way I'm moving. It only tells me which direction my acceleration is. Okay, so my acceleration is to the right, but my velocity is to the left. That means that I'm going to be slowing down. If your acceleration and your velocity are in opposite directions, you will slow down. If they're in the same direction, you will speed up. Okay, but I have these unbalanced forces in the x, in the y, they're balanced. So we're really looking at these graphs for my x direction horizontally. Okay, so horizontally, I would need to show a situation where the book is moving backwards, or maybe actually I'm going to define that as the positive direction. Okay, you can define your direction however you want. So I'm going to go ahead and say it's moving forward, and I'm going to say that my acceleration is going to be backward here. So I'm going to say moving forward slows down. It would look something like this. Okay, now could you define this as the negative direction? Sure, it's going to change the way that your graph looks. Okay, but if you did, you'd have something moving, you'd still have it slowing down, it would just be moving backwards. But again, you have to define your direction. Okay, so I have it moving forward, slowing down. On my VT graph, forward slowing down will look like this. On my AT graph, again, look at the slope of the VT. This is a negative slope, therefore it's a negative acceleration. Okay, so depending on how you define your positive direction, your graphs may or may not look exactly like this, but I would suggest that you write these down. Please make sure that you label that the positive direction in this example is to the left so that you understand why your graphs look like this. Yes?
The initial velocity will always be off that.
If you just have the free body diagram, you actually have no idea if you have an initial velocity or not, because you won't know which way you're going or how fast. So in a question like this, they'll have to tell you which way you're going if they want you to be able to analyze that information, and then you'll have to take a look at your free body diagram and figure out whether that means you're speeding up or slowing down. All right, so a couple questions to get you to think about some free body diagrams. It says choose one, more than one, or none at all. Which of these objects could be moving to the right? They're lettered A, B, C, D. Which one or which ones could be moving to the right? All of them is the answer. But yeah, sure, B. But all of them could be moving to the right. Okay, again, the free body diagram does not show you which way you are moving. It only shows you the direction of the acceleration. Okay, so any of these could be moving to the right. For that matter, any of them could be moving up. Okay, we don't know unless they give us some more information. Which ones could be accelerating? And not could be, which ones are accelerating? Yeah, B and D. Okay, the ones that have unbalanced forces, B and D, are going to be accelerating. A and C could be at rest. They could both be moving at constant speed. We don't know. They don't even have to have the same constant speed. But we don't know whether or not A is moving. We don't know whether or not C is moving. We do know that if they're moving, that they're moving at constant speed. Okay, that's what we know. Okay, same thing with these. If D is moving to the right, then it's speeding up. But if D is moving to the left, it's slowing down. Okay, so it depends on what other information they give you. Net force for each, A is going to be 0, B you're going to have 5 newtons to the right, C is going to be 0, and D will be 20 newtons to the right. Okay, so again, if you do have a net force both vertically and horizontally, which we haven't seen yet, then you'll have to draw in a resultant, a diagonal line to solve for it, but right now they're all in one dimension. All right, guys, for the rest of the class period, you are working on playlist 2. So go ahead and take a look at those task options or that checkpoint and get to work. If you have questions as you're working, please let me know.